Welcome to the second episode of the Dinosaur Stories podcast. Today's deep dive takes a massive stack of sources. We're looking at historical records, some pretty intense paleontology debates from Reddit, brand new biomechanical studies, and even high-stakes auction house data.
Yeah, it's quite the stack of material today.
It really is, and we're using all of it to extract the most surprising facts about one of the most famous dinosaurs to ever walk the Earth, the Triceratops.
Right, because we're synthesizing over a century of research here, literally right up to incredible discoveries published just this year, to reconstruct the actual day-to-day life of this animal.
And we really need to do this because you probably grew up with a very specific, almost cartoonish image of the Triceratops from movies and plastic toys.
Oh, absolutely.
You likely picture this slow, lumbering, solitary gray tank, right? Like, it essentially existed just to be locked in eternal face-to-face combat with a T-Rex.
Right, the classic showdown.
Exactly. But the latest science we're looking at today just completely shatters that illusion. We're looking at a highly complex, dynamic, shape-shifting, and migrating animal. Okay, let's unpack this.
Well, let's start by grounding ourselves in the physical reality of the animal first, because, its biology dictates literally everything else we're going to discuss today.
Makes sense.
So, we are situated in the late Cretaceous period. That's roughly 68 to 66 million years ago.
Right.
And the setting is the island continent of Laramidia, which today makes up Western North America. Now, the name Triceratops literally translates to three-horned face. But the sheer physical scale of this creature is, well, it's incredibly hard to conceptualize.
Yeah, because they were huge.
Right. We're talking about an animal that was 8 to 9 meters long, that's up to 30 feet, and tipping the scales at around 10 tons.
10 tons. Just to help you visualize that at home, you were looking at a creature that weighs roughly as much as a full-size school bus.
Mm-hmm.
But, compressed into a much denser, heavily armored, low-to-the-ground frame. And basic biology tells us that to keep a 10-ton body moving, you need fuel. Lots and lots of fuel.
Lots of fuel. They were primarily consuming tough, unforgiving, fibrous vegetation.
Like ancient palms and cycads, right?
Yeah, exactly. They had a very sharp, prominent beak at the front of their snouts, used for just aggressively plucking and snipping off heavy plant matter. But the real mechanical magic happened further back in the jaw.
Oh, the tooth batteries?
Right. They possess these massive, tightly packed tooth batteries containing anywhere from 430 to 800 individual teeth at any given time.
And these weren't just, standard issue teeth. There's a fascinating study in our sources by Professor Gregory Erickson that completely changes how we view their diet.
It's a brilliant study.
Right. Because if you look at modern animals that chew tough grasses like horses or bison, they have 4 distinct tissue layers in their teeth to handle the grinding.
Right, which is pretty standard for grazers.
Yeah. And crocodiles, which mostly just grab and swallow, they only have 2 layers. But the Triceratops had an unprecedented 5 tissue layers.
Which is an absolute marvel of evolutionary engineering. Because they were constantly chewing such dense, silica-heavy material, a normal tooth would just wear down to the gum line in no time.
It'd be useless.
Exactly. But those 5 complex layers were designed to wear away at completely different rates. This meant that as the animal chewed, the friction was literally self-sharpening the teeth.
Wow.
Yeah, they didn't just lazily mash their food. They possessed a highly efficient vertical shearing mechanism that could perfectly slice through the densest Cretaceous foliage day after day.
It's mechanical perfection. And speaking of mapping out their mechanics, the Melbourne Museum actually just acquired a wonderfully complete specimen.
Yes, they did.
And their goal is to create what they're calling a definitive atlas of anatomy. They want to finally lock down the exact vital stats of the species because, despite the Triceratops being so famous, there is still a massive amount we don't know about their exact proportions.
And understanding those exact physical proportions brings us to the most famous dynamic in all of paleontology, the supposed endless war between the Triceratops and the Tyrannosaurus rex.
Right, the Hollywood showdown we mentioned earlier. But there's this incredible debate we pulled from a paleontology community that really just completely deconstructs this myth.
It really does.
The myth being that the T-Rex just treated adult Triceratops like a standard, easy item on the dinner menu.
But wait, If the Triceratops is just this slow, heavy herbivore, how is a massive bipedal T-Rex not just picking them off easily?
Well, it comes down to basic ecosystem demographics and niche mathematics.
Okay, break that down for us.
So based on bone histology, it took a Triceratops roughly 10 years to reach its fully mature adult size. Furthermore, the general consensus is that their reproduction rates were relatively low.
Right, so they aren't like rabbits.
Exactly. Unlike some other dinosaurs, we simply don't find massive, sprawling clutches of eggs or huge herds of vulnerable babies. So if it takes you an entire decade to grow up, and your species isn't churning out hundreds of babies to play the numbers game, your adult mortality rate has to be extremely low for your species to avoid extinction.
Precisely.
Because if T-Rex was just effortlessly hunting and killing adult Triceratops every single day, the entire species would have collapsed. Yet, Triceratops is actually one of the most abundantly common dinosaurs we find in the Hell Creek Formation.
What's fascinating here is how the biomechanics perfectly support that incredibly low mortality rate. True macro predators, even today, like lions or tigers, they actually have surprisingly low hunting success rates.
Right.
A healthy, fully grown adult Triceratops was likely entirely off the regular menu because the physical risk to the predator was simply far too high.
Because the Triceratops was built for defense in a way that completely nullifies a bipedal predator.
Exactly.
It goes back to an analogy we found. It's like a tall person trying to wrestle a forklift.
That's a great way to picture it.
Right? They had a very low center of gravity. They had widely spread toes designed for maximum traction in the dirt. And critically, they had a ball-and-socket neck joint.
Which is huge for mobility.
Yeah, that joint meant they could pivot that massive, heavily armed head incredibly fast in almost any direction. So imagine a T-Rex trying to attack.
It's not an easy fight.
No.
Yeah.
It has to bend down, totally exposing its own neck and chest to get into the danger zone of those meter-long horns. The leverage is just completely wrong for the predator.
Precisely. The bipedal nature of the T-Rex actively works against it here, and the physical fossil evidence of T-Rex eating Triceratops actually points heavily towards scavenging, not active hunting.
Which makes sense.
Paleontologist Mark P. Whitten has a brilliant model regarding this. We frequently find fossils showing deep T-Rex tooth marks on Triceratops pelvises and on their bony neck frills.
Right, and think about how predators operate. You eat the prime, nutrient-dense meat first, right? The hindquarters.
Right.
You absolutely do not start your meal by biting into a massive, tough, solid bone frill, or risking your own teeth trying to pull an 8-ton head off the body just to get a tiny scrap of neck meat.
No, you wouldn't.
The only reason a T-Rex would be gnawing on the frill is if all the prime meat was already eaten.
Exactly. If a T-Rex is biting a bony frill, it strongly suggests it stumbled upon a carcass that was already picked clean, or it was desperately scavenging. Taking down a prime, healthy, 10-ton adult Triceratops head-on would have been an absolute last resort, life-threatening gamble for a T-Rex.
So if the T-Rex wasn't their primary danger, what was? Well, the fossils themselves give us the answer. And it turns out their biggest threat was each other.
Yes, intraspecific combat.
And we can see this perfectly in one of the most famous recent specimens in the world, a dinosaur named Big John.
Big John is a truly remarkable discovery. It was unearthed in 2014 in the Hell Creek Formation of South Dakota by fossil hunter Walter Stein.
And affectionately named after the owner of the ranch where it was found, right?
Right. The entire skeleton is over 60% complete, and even more critically, the skull is 75% complete.
I was reading the stats on Big John, and they are just staggering. The fossilized bones alone, way over 1,500 pounds.
It's massive.
But how do paleontologists get from 1,500 pounds of fossil to visualizing a 10-ton living animal?
That requires some complex extrapolation. Paleontologists examine the bone density, but more importantly, they look at the muscle attachment points.
Like the collarbone.
Yes. For instance, Big John has a collarbone measuring an unbelievable 2.62 meters. You only need a collarbone that massive if it needs to serve as the anchor point for the colossal, incredibly thick muscles required to hold up a head that heavy.
That's just wild.
And when the Zoic workshop in Italy finally assembled the skeleton, modeling its dynamic posture after the Wall Street Charging Bull, interestingly enough, they determined Big John is 5 to 10% larger than any other known specimen. Its top horns are over a meter long.
But the real story isn't just his size, it's what he survived. Our sources note a very specific injury on his squamosal bone. Can you explain what and where that is?
Certainly. The squamosal bone is a large plate forming the outer margin of that massive neck frill. On Big John's right squamosal bone, researchers found a keyhole-shaped puncture wound, roughly 20 by 5 centimeters.
A combat lesion.
Most likely, yes.
So most likely a direct strike from the meter-long horn of a rival Triceratops during a fight. But how do we know that strike wasn't what killed him?
Because of the microscopic evidence left behind, researchers took samples from the edges of that puncture and placed them under an electron microscope.
And what did they find?
They discovered porous, highly disorganized new bone growth around the margins of the wound.
Oh, so it was healing.
Exactly. Bone remodeling is a slow process. The body has to send specialized cells called osteoblasts to the area to literally weave new bone tissue over the trauma. The presence of this specific growth tells us Big John survived that brutal strike and lived for at least 6 months afterward.
It is just wild to imagine a meter-long horn violently punching through solid bone, and the animal just shakes it off, heals, and keeps walking for months.
He was a tough animal.
Big John was an incredible survivor, although his journey didn't end in the Cretaceous. He recently made massive waves in the financial world.
Yes, the modern chapter of Big John's story is quite different. The skeleton was sold at the Hotel Drouot auction in Paris for 6.6 million euros.
Which is about 7.7 million US dollars at the time.
Right. The buyer was a U.S. collector named Siddhartha Pajitapati, who has since loaned it to the Glazer Children's Museum in Tampa so the public can see it.
And this kind of auction always sparks a massive, very heated debate in the paleontology world.
If we connect this to the bigger picture, the sale of specimens like Big John highlights a very real tension in modern science.
Yeah, the private versus public debate.
It is an objective fact that wealthy private collectors are injecting millions of dollars into the costly excavation and careful preparation of these fossils, bringing to light specimens that might otherwise just erode away.
Right.
However, it is equally true that these skyrocketing multi-million-dollar prices completely price publicly funded museums and universities out of the market.
Which is a huge problem for researchers.
Exactly. The core fear among scientists is that this private market trend makes crucial, one-of-a-kind specimens inaccessible for rigorous peer-review research because a private owner always has the legal right to restrict access.
It's a complex modern reality with no easy answers.
Yeah.
But, setting the auction drama aside, Big John's biology highlights something else that's crucial. Extreme old age.
Yes.
They estimate Big John was around 60 years old when he finally died. And age is actually at the center of arguably the most vicious civil war in the history of paleontology.
Ah, yes. The identity crisis of the Triceratops.
The identity crisis. The core issue is that as these ceratopsians age, their skull bones don't just scale up and get uniformly larger. They literally stretch, resorb, and change their entire geometric shape. And to be fair, humans have been confused by these bones since day one. When O.C. Marsh first found a pair of Triceratops horns in 1887, he didn't even think it was a dinosaur.
No, he didn't.
He confidently proclaimed they belonged to a giant extinct bison, which he named Bison alticornis.
It took time to even realize they were horned dinosaurs, but even after that, the classifications were a mess.
Paleontologists used to think there were dozens of different species of Triceratops based on slightly different skull shapes, right?
Yes. But a landmark 2014 study by John Scannella helped clean up the family tree.
Okay, how so?
Well, he showed that one older species, Triceratops horridus, which featured a small nose horn and a long beak, actually evolved directly into Triceratops prorsus, which had a long nose horn and a short beak.
Oh, wow.
And this evolutionary shift happened right there in the Hell Creek Formation over a period of about 1 to 2 million years.
Okay, so that handles the evolution from one species into another over millions of years. Here's where it gets really interesting. What happens when a single individual Triceratops just gets really, really old?
Enter the Torosaurus debate.
Yes. So historically, the Torosaurus was classified as a completely separate genus of horned dinosaur.
Right. It lived at the exact same time in the exact same environments, but it had a vastly larger, much longer frill that contained 2 massive holes known as fenestrae.
But then Scannella and the legendary paleontologist Jack Horner dropped an absolute bombshell in the scientific community.
They certainly did.
They proposed that Torosaurus wasn't a separate species at all. They argued that Torosaurus was actually just the fully mature, elderly grandpa stage of the Triceratops.
Their argument relies heavily on the specific nature of ceratopsian skulls, which are composed of something called metaplastic bone.
Metaplastic bone.
Yeah. Unlike human bone, which sets and stays relatively fixed in shape once we reach adulthood, think of metaplastic bone almost like biological clay that never fully dries out.
That is wild.
Over the decades of the animal's life, the body can continuously mold, stretch, and reshape it. Scannella and Horner argued that as a Triceratops reached extreme old age, like 60 or 70 years old, its solid frill would stretch backward to immense lengths.
Right, and to offset the incredible unmanageable weight of that lengthened bone, the frill would thin out in certain areas and eventually open up into those large holes.
Exactly.
Wait, so are you telling me that for over a century we might have been looking at a senior citizen Triceratops and mistakenly calling it a completely different animal?
That is exactly the bold proposal they put forward. However, the wider scientific community pushed back, and they pushed back incredibly hard.
I don't know.
Researchers like Andrew Fark, Nicholas Longrich, and Daniel Field analyzed the fossil data and pointed out some major, potentially fatal flaws in the theory.
Right, and the counter-arguments make a lot of logical sense. If Torosaurus is just an elderly Triceratops, shouldn't we be finding teenagers that are halfway through the morphing process? And even more importantly, they actually found juvenile Torosaurus specimens. I mean, if Torosaurus is purely an end-of-life stage, a juvenile version shouldn't even exist.
Right. Furthermore, those researchers pointed out that the two forms aren't always found in the exact same geographic layers. There's spatial separation.
Oh, interesting.
And regarding the supposed transitional species that Horner pointed to, a fossil called Nidoceratops, which had smaller, irregular holes in its frill. Longrich and Field argued that specific specimen likely just suffered from a severe bone disease or injury.
Oh, so rather than representing a natural missing link in a growth stage, it was just sick.
Exactly.
So while the idea of a shape-shifting, morphing skull is incredible, the jury is definitely still out, with a lot of heavy hitters leaning toward them remaining separate species.
It's still a very active debate.
But the fact that their skulls were these massive, biologically dynamic structures naturally leads me to wonder how they actually used them. Like, what was going on inside that massive head? How smart were they?
Well, by using advanced computed tomography CT scans, researchers have been able to map the internal brain cases.
And what did they find?
The scans reveal that their brains were quite small relative to their immense body size. We definitely shouldn't think of them as possessing elephant-level social complexity or high intelligence.
So not dinosaur geniuses.
No, their cognitive abilities were perhaps more akin to modern herding animals like cattle or buffalo.
Okay, the scans also showed they had a relatively poor sense of smell. But their cochlear length, the specific part of the inner ear responsible for processing hearing, was quite short.
Right.
And in the broader animal kingdom, a shorter cochlear length is a direct adaptation for hearing low-frequency sounds.
Which is a vital clue for understanding their social structure. For a long time, because adult Triceratops fossils were almost always found alone, the consensus was that they were strictly solitary animals.
Yeah, just wandering around by themselves.
Yeah. But in 2013, a team from the Naturalist Biodiversity Center made a paradigm-shifting discovery in Wyoming. They unearthed a single bone bed containing 5 Triceratops of varying ages that had all died together, mired in a muddy swamp.
5 of them dying at the exact same time in the exact same place. I mean, that heavily implies they were traveling together as a family group.
It does.
And researchers actually proved they had a shared migratory existence by looking at the stable isotopes in their teeth. But how exactly does an isotope prove migration?
Think of stable isotopes almost like a chemical passport stamp.
Okay.
As an animal drinks local groundwater and eats local vegetation, the unique chemical signature of that specific geographic region gets locked into the layers of their growing teeth.
Oh, that makes sense.
Because all 5 of these Triceratops had the exact same sequence of passport stamps layered into their teeth, we know unequivocally that they were moving through the same environments together over a long period.
They were a herd, a migrating herd of 10-ton armored giants. But if they're migrating across the harsh, late Cretaceous landscape, hauling a 10-ton body and the largest solid skull of any land animal, it sounds like an absolute thermal nightmare.
This raises an important question regarding their core biology. Whether they were fully endothermic, meaning warm-blooded, or gigantothermic, where their sheer, massive bulk physically traps heat inside the body.
Right.
Standing under the intense Cretaceous sun in a giant armored frame is incredibly dangerous. Overheating was a constant, lethal threat.
Which perfectly sets up a groundbreaking 2026 study out of the University of Tokyo by researcher Seishiro Tada.
Yes.
They used highly advanced CT scans to look inside the massive snout of the Triceratops. Now, in most reptiles, the nerves and blood vessels travel safely through the jaw to reach the
That's
nose.
the normal pathway.
But the Triceratops skull is so incredibly massive and specialized that the sheer density of the bone actually blocked that normal pathway.
So evolution had to find a biological workaround. The nerves and blood vessels bypass the jaw entirely, taking a complex route through the nasal cavity.
Blah.
But that routing wasn't even the biggest discovery. When they scanned the internasal cavities, they found clear evidence of what are called respiratory turbinates.
And what exactly does a respiratory turbinate do?
Respiratory turbinates are intricate, complex networks of thin bone and soft tissue located inside the nasal passage.
Okay.
As the animal breathes in hot or dry air, this dense network of tissue acts to regulate the heat and moisture of that air before it reaches the lungs, and it cools the blood traveling to the brain.
No way.
It essentially functions as a highly efficient biological air conditioning unit.
A high-tech cooling system hidden right in the middle of their face.
Exactly.
That massive nose wasn't for smelling. We already established their sense of smell was poor. It was a radiator,
Yes, it was.
working in tandem with that giant neck frill, which was thoroughly pumped full of blood vessels. The Triceratops possessed a highly advanced thermoregulatory system specifically designed to keep its brain from literally cooking inside its own skull.
It's brilliant. It forces us to view the animal not as some blunt, primitive, evolutionary dead end, but as an incredibly refined, highly adapted biological machine.
Absolutely.
From the self-sharpening mechanics of its 5-layer teeth to the internal climate control of its massive skull.
So what does this all mean? I want you to take a second and completely rethink the dinosaur you thought you knew. Throw away that childhood image of the slow, solitary, boring gray tank just waiting around in a swamp for a T-Rex to show up. It wasn't just a victim.
Not at all. Instead, you should picture a highly successful, incredibly dynamic animal, one that migrated across continents and family groups.
Right.
An animal robust enough to take a meter-long horn directly to the skull, heal the shattered bone, and keep walking for months.
Feel like Big John.
Exactly. An animal equipped with an air conditioner in its nose and a lifespan so long that its very skull literally morphed, stretched, and reshaped itself as it aged into a senior citizen.
It's a complete perspective shift. And I want to leave you with one final provocative thought to mull over.
Oh, please do.
We now know they lived and traveled in herds. We know from the length of their inner ears that they heard in deep, low frequencies. And we know they had those massive neck frills pumped completely full of blood vessels,
Right.
which likely meant they could flush them with vibrant color for mating or display. So what if the late Cretaceous wasn't just a dusty world of roaring, shrieking gray monsters?
I love this thought.
What if instead it was a landscape filled with vibrant, brightly colored frills flashing brilliantly in the sun? And what if the primary sound of that world wasn't a terrifying roar, but deep, rumbling, low-frequency vibrations, a sound you could actually feel vibrating right in your chest long before you ever saw the herd cresting the hill?
That's an incredible image.
We only have their fossilized silent bones to look at today, but the real world they lived in was likely a loud, vibrant, colorful, and completely alien landscape.